So I remember watching a Vsauce video about the Monty Hall problem a few years ago, but I did not really understand it very well. Probably because I didn't pay proper attention back then. Anyway, I watched the same video again a few days ago, and now I think I do understand what the reason might be, and would like to explore it further. For the people who haven't heard of the problem before, I'll give a quick explanation. So the basic idea is that there are three doors with a reward being behind one of them. Let's call it the cash door. The other two doors do not contain anything of value. Let's call them trash doors. You as the player are unaware of which door is which, obviously, but the host knows what's behind each door. The host asks the player to pick a door. Let's say out of the doors A, B and C, you pick door A. Now at this point, remember that you only get to pick the door. You do not get to see what's behind it. Among the remaining doors, B and C in this case, the host opens a door which will always have trash behind it. Now the host gives the player the option to switch. Say if he revealed door B as one of the trash doors, the player can either stick to his original choice A or change the pick to door C. Now the core question of the problem is whether you should switch or not. The answer is that you should always switch. It may not feel intuitive at first, but I'll try to explain how I managed to wrap my head around it. And as a disclaimer, this is more of a let's try to understand the problem together sort of a video than a pure explainer. I'm not a mathematician, hell I'm not even good at maths, so just keep that in mind. I'll just show you the simulations and graphs of a couple of different variations of the problem, which helped me get an intuition for it. Let's consider 49 doors instead of 3. Now the most common extension or variation of this problem is the one where the host will open all doors but one out of the remaining doors. So in this case, after the first pick is made by the player, he would open 47 of the 48 remaining doors. Remember that the host can open only the doors that have trash behind them. In our little simulation here, the player makes his first choice by picking the box that just turned white. Here the boxes serve the same purpose as the doors. Now keep in mind that this box has not been opened yet. It is just the one that the player has guessed to be the cash box. It has of course been picked at random essentially, with the chances of it having the cash being 1 in 49, that is 2.04%. The probability of the cash being in the set of all the remaining boxes will therefore be 97.96%. So when the host reveals 47 of the 48 remaining boxes as the ones containing trash one after the other, like so, the probability of the entire set of these remaining 48 boxes having the cash gets concentrated on the one remaining box. In other words, the probability of the cash box being any one of the boxes that is not the first choice sort of collapses on just this one remaining box. And it does indeed have the cash in it. Your initial pick may have the cash, yes, but the odds will not be in your favor if you do not switch. Let's repeat it for a total of 9 boxes now. The probabilities are as shown on the screen. Notice how as the number of boxes or doors decreases, the probability of your first pick being the correct one increases, which is pretty obvious. This is a fine way to look at it, and it has been used in countless explanations, but it was not the first one that I thought of. The one that came to my mind was another just as simple variation of the problem that can also help build some intuition. With the more common and perhaps the more logically sound variation that we just saw, the thing is that as the number of boxes increases, the probability of you winning by switching also increases, as it is proportional to your first guess being incorrect. But the original problem with 3 doors can be seen as either 1, the host revealing all doors but one out of the other doors, and 2, the host revealing half of the other doors, because 2 minus 1 is the same as 2 over 2, which is half of 2. If we consider the latter variation of the game, where only half of the other doors are revealed after the initial choice is made, then if the player decides to make a switch, he has to make a guess again out of the remaining doors. In this case, the probability of the player being correct even after switching decreases as the total number of doors increases. But more importantly, it still consistently remains above the probability of the first choice being the correct one. This is because the chances of the first choice being correct for n doors will still be 1 over n, but for switching it can be evaluated by the following formula, which simplifies to 2 over n, while it is n minus 1 over n for the former variation. So as the number of trash doors revealed for any given n increases, the chances of winning by switching also increase. This graph shows the probabilities calculated from the results of running the same simulation multiple times for n number of doors, and as you can see, the former variation follows a divergent pattern between staying with the initial choice and switching, while the latter follows a convergent pattern where switching is still always beneficial to the player, and the results of both variations meet when the number of doors is 3. So finally, the original problem can be seen in the following manner. There is a 1 in 3 chance of the cache being behind your first pick, that is door A, and there is a 2 in 3 chance of the cache being behind either door B or door C. So when the host knowingly and deliberately eliminates door B by opening it and revealing it as one of the trash doors, that 2 in 3 chance gets reassigned to just door C. So in the end, there is a 33.33% chance of winning by staying with the original choice and a 66.67% chance of winning by switching.